I'm blue, I've been need, I've been died, I've been need, I've been died, I've been need, I've been.
Differential equation is an equation that relates one or more functions and their derivative. Differential equations are very important in the mathematical modeling of physical systems. Many fundamental laws of physics and chemistry can be formulated as differential equations. In biology and economics, differential equations are used to model the behavior of complex systems. Differential equations are important in application in daily life. They are used in a wide variety of disciplines from biology, economics, physics, chemistry, and engineering. They can describe exponential growth and decay, the population growth of species, of the change in investment return over time. I want to share about the application of differential equation, which is glucose absorption by the body. Absorption of glucose entails transport from the intestinal lumen across the epithelium and into blood. The transporter that carries glucose and galactose into the enterocyte is the sodium-dependent hexose transporter, or SGLUT1. A computer model simulating human glucose absorption and metabolism in health and metabolic disease states. A computer model designed to simulate integrate glucose-dependent change in splenic blood flow with a small intestinal glucose absorption and hormonal and incretin secretion and hepatic and systemic metabolism in health and metabolic disease. The model of glucose absorption and metabolism was created with several aims: to provide a quantitative simulation of the effect of the change of capillary perfusions, to provide a broader understanding on how incretins affect the whole body response to glucose, and to demonstrate how metabolic disease and uptake and metabolism. This is the example solution that we use differential equations, glucose equations, insulin equations, and incretin submodel and glucagon submodel. There are four main components of the model of glucose circulation and metabolism, which is systemic glucose metabolism, insulin flow submodel, glucagon submodel, and GLP-1 submodel. Systemic glucose metabolism. Glucose enters into the systemic circulation through the hepatic vein. It is metabolized by either insulin-dependent process in muscle and adipose tissue. Insulin flow submodel shows that insulin is released by pancreatic islet beta cells into a superior mesenteric blood compartment, partially in response to a micro-segmental function of systemic arterial glucose concentrations. Glucagon is same like insulin, while GLP-1 submodel is contrast with glucagon and insulins, which are sensitive to systemic arterial glucose. Panels show 3D surface plots of the effect of two variable GLP-1 glucose sensitivity with change in splenic glucose concentration and intestinal pericellular glucose permeability. The interaction between these variables is shown as the coefficient C. On the panels show pair effect contrasting the interactions at peak splenic glucose flow with those during when splenic glucose is at minimal value. LA shows that SMA flow after feeding increases as a linear function of GLP-1 and as a hyperbolic function, and the interaction coefficient C for 4.1, indicating a strong positive interaction between P and GLP-1 secretion, as can be seen from the upward elevation of the surface towards higher values of both independent variables. It shows during fasting, in contrast to effect seen with feeding in a panel A. There is no effect of altering P, although SMA increase with GLP-1 secretion. Coefficient C equal to 0 when intestinal glucose absorption is absent. Panel C shows there is a synergistic response of portal, blood flow, and glucose flow as a result of the interaction between P and GLP-1 secretion, which leads to both increases splenic blood flow and glucose concentration. C equal to 2.74. For the last one, panels F and G shows as with SMA flow, C panel A and B portal vein flows increase synergistically with increases in GLP-1 and P during when glucose is present in the splenic circulation. C equal to 4.15, but during fasting P effect are absent. C equal to 0. That's all from me.